Well, finishing up chapter 2, we're going to look in sections 2.5 and 2.6. And right before this, remember all we were doing was just covering the whole topic of functions. And for a graph or an equation to be called a function, we know it has to pass the vertical line test if you're looking at the graph. And then if it passes the vertical line test, or for the equation itself, means that for every value I plug in, if I plug in one value, I only get one value coming out. So if that happens, then we know we have a function and we can use a special function notation, like remember we were looking at the f of x or g of x, or it could even be p of t depending on what's going on. Okay, well here in 2.5 and 2.6 we're going to focus on two of the functions, two very popular functions. One's the linear function and the other one's a quadratic function. A linear function is just like a linear equation. It's the equation in the form of y equals mx plus b. So we know for a fact that if I have an equation that's in y equal mx plus b, I know it's linear because the powers on the both variables, the x and the y, are both 1. And just as kind of devil's advocate here, look at this little note I have written. For y equals the square root of x plus 3, what is the power on x? Well, you're like, okay, it's sitting underneath this radical with a power of 1. So it's got to be just a power of 1, therefore this is linear. But no, do you remember back in chapter 1 when we talked about fractional exponents? Do you remember how fractional exponents, what they refer to, are radicals? So this right here, the power on x is actually the 1/2 power. The 1 is because that's the power of x inside the radical, but the 2 because this is the square root. Okay, so just remember that. So really, y equals the square root of x plus 3 is definitely not linear because the power is not 1. The power is actually 1/2 on that variable. Okay, the other type of function that we're going to look at here in this last bit of chapter 2 is the quadratic function. And specifically for quadratic, it just means that either, if you have it in the form of y equals ax squared plus bx plus c, then you have, at least an x squared term in there. Or the other way around, if it's x equals, then you have at least a y squared term in there. So either x or y is squared, but not both. If both are squared, you actually have a circle. So just keep in mind that if only either just an x is squared or just a y is squared, then you have a quadratic equation. And when you graph a quadratic equation, what you're going to get is that parabola. It'll be a parabola facing up or a parabola facing down if what's squared is the x. It's going to be a parabola facing to the right or a parabola facing to the left if what's being squared is the y. So this would be an example of an x squared, and this is an example of a y squared. All right, let's go to example number 1. Here in example 1, they're going to give you just a sample of equations. Looks like we have about 4 of them, and we just want to circle the ones that are linear. So going to this first example, the 2x equals 3y plus 8. Well, the x is to the first power, the y is to the first power, so I'm going to circle this because it's definitely linear. Now if I go to this next one, this really is 3x to the 1/2 power plus 4y equals 0. So the y is to the first, but because the x is to the 1/2, this is definitely not linear. If we go to the third one, it's 2x to the first and y to the first, so this is linear right here. And then on this last one, 2x minus 3y squared, because of that, this one's nonlinear. Okay, and just to kind of play one more, I just thought of one I wanted to kind of show you guys. What if it had, let's say 2 over x plus 3y is equal to 1? Would that one be linear? Well, if we look, remember anytime you have a variable in the denominator, it really isn't to the first power because this problem right here is the exact same thing as 2x to the negative 1 plus 3y equals 1. So when you have a variable in the denominator, it really doesn't have an exponent of 1. It has an exponent of 1, but it's actually negative. So this one right here is definitely nonlinear. All right, so just another thought to keep in mind. Let's go on to example number 2, though. Here in example 2, a manufacturer has a monthly fixed cost of $40,000 and a production cost of $8 for each unit produced. And if the product sells for $12 per unit. Okay, we're going to find a couple answers here. First of all, we want to list out a cost function. And just like what we did in some of the problems in the last session, we know that cost can sometimes be broken down into 2 parts. We can have a fixed cost. Those incorporate like mortgage and salaries, things like that. And then we can have variable costs. And variable costs refer to things that change according. So supply costs, bills, electricity, the water. It changes according to usage, okay? So when we're really looking at the cost function, just remember that this is variable cost plus fixed costs. Okay, this is pretty much the only part where you're ever going to have two portions together. So we can write our cost function. Let's say, for example, X equals the number of units sold or units produced. Okay, so a reason why I want to know that is I'm trying to declare my variables. So our cost function, C of X, cost depending on how many units I produce, is going to equal to, well, do we have a fixed cost? Of course we do. It says it has a monthly fixed cost of $40,000. And then let's look at variable cost. And it says it has a production cost of $8 for each unit produced. So $8 per unit would be 8x. And there's the example of what the cost function would look like. Now the revenue function, I'll do capital R for revenue. Revenue is a function of X. It's the function of the number of units produced. How much money do we make every time we sell one of these units? Well, we're making $12 per unit, so 12x. Remember, always multiplication means per. All right, going down to the next part here. It says, what is the profit function? Okay, well the profit, remember profit, by definition, we can say that P of X is always the amount in, the revenue, minus the amount you have to spend to get out. So it's the revenue, it's 12x, minus, and I'm about to subtract the cost function. Because the cost function has more than one term, I've got to be very, very careful and make sure I put it behind parentheses. This is not a hard subject whatsoever, but it's just realizing if you ever put more than one term behind a minus sign, you've got to put it in parentheses because I want to make sure I'm subtracting all of the cost function, not just the fixed, not just the variable, but actually all of the cost function. So by the time I do that and combine like terms, a 12x minus an 8x is 4x, and then minus 40,000. So there's the profit function right there. Okay. Now let's go on to the next part. It's going to kind of keep going with this whole idea. It says find and interpret P of 12,000. Well, luckily since we named our functions, we know P of 12,000 is saying, well, what's the profit at 12,000? So P of 12,000 is going to equal 4 times 12,000 minus 40,000. Well, 12 times 4 is 48, so 12,000 times 4 is 48,000, minus 40,000 would be 8,000. So basically, if we want to interpret this, the profit of producing, just a second, let me make sure I spell this right. The profit of producing 12,000 units is $8,000. Not too bad. All right, let's go on to the next topic. Okay, well, as we're about to see in the future chapters, and specifically now, we're talking about this thing called the intersection. And intersection is, take it from the real world, put it into the math, and it means the exact same thing. An intersection is just a crossover of two things. So in this, what we're talking about specifically is a crossover between two graphs. You can take a line and cross it with a parabola, so they'll probably hit each other twice. Or you can take two lines where they might hit each other once. But in the world of business, we call this point where two lines or two graphs intersect, we call it the break-even point. And specifically, if we use really business terms, the break-even point right here, that's the point where cost equals revenue. So in other words, when there is absolutely no profit. When you think about it, when a business breaks even, if they just at the very end of the year finally break even, it means all the money they spent making a product and all the money that came in when they sold it is completely equal. We had absolutely no profit. So definitely something you don't want to have, but it's nice to know exactly where that break-even point is, because as soon as you start selling one more item, then you know you've broken into the profits. So it's very, very, very popular for businesses to come to mathematicians and say, what do I have to do to break even? What do I have to do to find this out? Okay? And how we're going to, there's a big key right here, how we're going to go about finding this break-even point is you're going to set the equations equal to each other. Okay, so let's go to example number 3 so we can kind of get an idea of what we're doing here. We want to find the point of intersection between 2x plus 4y equals 11 and negative 5x plus 3y equals 5. Okay, so we have two lines. Obviously, two lines can intersect at most at one point, or unless they're the exact same one, and then in that case they're lying on top of each other, but we're looking for one point of intersection here. And it says up there, right above in the sentence, it says intersection points are found by setting the equations equal to each other. Well, you have to do one step first. You've got to have them both as x equals or y equals. We're really great by the time we got through all of our graphing stuff, we're really awesome at solving for y. So why don't we do this? Let's move the x's over. We'll get 4y is equal to negative 2x plus 11. And let's divide by 4 everything through. So I have y is equal to, let's say, negative x over 2 plus 11 over 4. Okay, so that's the first equation. Now let's go the same thing with the second equation. Got negative 5x plus 3y is equal to 5. Move that guy over, so 3y is equal to 5x plus 5. Dividing by 3 on everything to make sure we do all of our rules. We get 5x over 3 plus 5/3. Okay, so you know how it says here on the left, we have an equation that basically says y equals this, and then we have another one that says, well, y equals this. So because they're now in the form of y equals and y equals, then we can take the two parts on the right and set them equal to each other. So negative x over 2 plus 11 over 4 is equal to 5x over 3 plus 5 over 3. Just like that. And this is what you're going to do every single time. So take those two equations, make sure they're solved for the same variable, and then set the other parts equal to each other. And then just solve. Well, I've got a ton of fractions, and I hate fractions, so let's eliminate these things. Between 2, 4, and 3, looks like the LCD would be 12. So we're going to multiply everything through by 12. So I can do one, if you want to kind of, since we've got practice with this, if we want to kind of do it as we go along. If I go 12 times x, a negative x, you'll get negative 12x over 2, which makes a negative 6x. I know that 4 will go into 12 3 times, so 3 times 11 is 33. 3 goes into 12 4 times, and 4 times 5 is 20x. Again, 3 into 12 is 4, and 4 times 5 is 20. Okay, and just like that, everything's reduced. So let's group all of our x's together. Let's put all of our constants together. So a negative 6, and when I move the 20 over, it's going to be a negative 20x. And when I move that 33 over, it'll be a negative 33. Okay, so negative 6 and a negative 20 is a negative 26. And 20 minus 33 is negative 13. Let's divide off that negative 26. And we get x to be 1/2. Okay, well, I'm not fully done with my answer because our goal here is to find a coordinate. Because where two lines are intersecting, they don't intersect at just an x value, they intersect at a coordinate. So I need an x value and a y value. How am I going to get that y value? I can go back and plug it into any one of the original equations, and that's what I would do. Okay, so let me give myself some room for just 1 second. Say I just choose to use that first one. So 2x plus 4y equals 11. Now I know what x is, so 2 times 1/2 plus 4y equals 11. Well, half of 2 is 1, plus 4y equals 11. Let's move that 1 over, so 4y equals 10. And then dividing both sides by 4, you get a y value, reducing that of 5/2. So together, we have the coordinate an x value of 1/2, a y value of 5/2. Box that up, and there's our overall answer right there. That is the intersection between those 2 points. Okay, let's go try this one more time and go to example number 4.